Hello, H-Trick students. Mr. Meunier here. Going to start up our new unit on vectors. The note sheet I'm looking at you can find in your day 13, April 13 folder here in Schoology. I also have a keyed in version of this note sheet in that folder. Understand that with our new shortened schedule going 3 days a week, and we're ending on Friday, May 22nd now, I'm going to I will be cutting some material out, shortening things up, trying to do more of the bare essential work throughout this unit on vectors, and our last unit, which will basically be in the month of May, on polar coordinates, polar equations. So with these notes, I'm not going to do every single example we see here. If I do not cover it in the notes, you're not going to be responsible for it on any quizzes or future unit tests. So try to follow along with the video and focus on what I refer to and what I do, because I will be cutting material out. Your chapter 8 test looked fantastic. Put those in the grade book. Well done. I spun a slight curve on it just because of the situation we're going through right now. I don't want anybody's grades to be hindered because of this e-learning endeavor that we're going through. So that's why your Schoology score you saw might not quite exactly match the gradebook score. You guys did not need a curve whatsoever. You guys did a wonderful job on that. So moving forward here, I would expect a couple of lessons Monday, Wednesday, most weeks, with a Friday quiz covering that week's material, and probably a unit test at the end of April and a unit test at the end of May. All right, so moving forward here. Vectors. Vector. If you've been in physics class, you've probably seen a lot of this material. If you haven't been in physics, it's going to be maybe brand new to you. But a vector is just a tool to measure the size and direction of some action. So every vector has magnitude. Magnitude is the size, and direction, that is where it is moving. That's typically, an angle of some sort. So a vector, again, has a magnitude and a direction, a size and an angle. And those could represent a lot of things. It could be an airplane is flying 500 miles per hour. That's a magnitude at a direction of 30 degrees. That's an angle. It could be I am pulling a rope with a force of 15 newtons at an angle of 20 degrees. It could be you move 10 miles at an angle of 90 degrees. Again, if you have a size and a direction together, that makes a vector. We are going to kind of skip by what's called geometric vectors here. Geometric vectors, basically, long story short, is a picture of what is happening. So this is a geometric vector where we physically draw something out. And again, this vector has a magnitude, there's a size to it, and it's pointed at a certain angle. Every vector has an initial point and a terminal point. Initial point being where you start, and a terminal being where we end. We're going to start this particular vector at point P and end it at point Q. And where you start and where you stop is important with a vector. With this, we tend to use a ray to denote that. There's an arrow at the terminal point of a vector and just a point at the initial point. So this goes from P to Q, arrow indicating the direction in which it's moving in. To label this vector, a few things could happen. Sometimes they use PQ. We start at P, we stop at Q, in that order. Sometimes they'll give a lowercase letter, vector A here, to represent that, vector A. Those are two ways. That symbol might be kind of hard to see. That's an A with that type of symbol above it. Whoops, and that didn't work out very well. Something like that. Or again, PQ with a symbol above it. The magnitude of a vector, the size of it's typically denoted by an absolute value symbol. So that magnitude of A, if you see something like that, that means how big is vector A. Or your book, a lot of times will use a double absolute value symbol to denote that. That double absolute value symbol is really just used to differentiate the fact that absolute value we tend to use to denote to flip a negative, the distance, the displacement something has from 0. Double absolute value symbol is a little more vector specific in your particular textbook. All righty. So moving on here. A lot of times we put vectors in standard position. That just means, you know, we use our normal 0 degrees as positive x-axis, 90 degrees as positive y-axis. A lot of things we do, and our direction feeds off of that standard position. Moving up is a positive angle, down is a negative angle. The 0 vector has no magnitude, and it can be any direction. It's basically a point. It does not move anywhere. The 0 vector is a point. We're not going to get into getting protractors and rulers out now like we would have before. But if I wanted to measure this vector, I would lay down a ruler, measure how large is this vector, put down a protractor, and measure what angle is that vector pointed at. So vector in there. It is important to know that two vectors are equal if and only if they have the exact same magnitude and the exact same direction. I'm not going to run through all of these cases, but for instance, eyeballing this without a ruler or protractor, I would say vector z and vector y are equal to each other. They appear to have the exact same size, and they appear to be pointing the exact same direction. Which have the same direction yet are not equal. Just one case of this, I'm not going to go through all of them, would be vector x and vector w. X and w are both pointed out towards 0 degrees, but they are not the same size. And which vectors have the same magnitude but are not equal? I would say v and w, maybe. There's a lot of those, but it looks like v and w are roughly the same size, but they're clearly not pointing the same direction, so they are not equal. Both components need to come together. They're equal if and only if you have the same direction and the same magnitude. Magnitude is how large it is, direction is where it is pointed. Every vector, again, has an initial, a start value, and a terminal, a stop value. Arrow is directing you towards that stop value. All right. So moving on. We can put vectors together, and that is really a common tool that you're going to be using in a lot of physics classes. If an airplane flies, that is a vector. If the wind is blowing, that is another vector. When the plane and the wind interact with each other, you kind of get blown off course. The sum of those is called the resultant. Resultant, again, is the sum of two or more vectors. What happens when the plane and the wind come together? Where are you actually moving? And we can physically draw that out with geometric vectors. Again, we're going to do kind of a crash course on this. I'm not going to hold you responsible for drawing vectors out, but I would feel remiss if I didn't show you at least the triangle method to sketch out vectors physically. So if we have vector v and vector w shown here, we can add these together. I'm going to do v plus w, vector v plus vector w. And all we do is we lay down vector v, eyeball it somewhat. I would say that's what vector v looks like. We're going to build a triangle. So at the end of vector v, we're going to place vector w. So vector v ends at this arrow. I'm going to start vector w, and it's going to move down and to the right, like so. So we could imagine maybe that vector v represents an airplane flying. Vector w could represent the wind blowing. And common sense says that wind's going to kind of blow the airplane off course. And we can draw that by completing this triangle. If I go from the beginning of vector v, the start of this entire situation, to the end of vector w, the final resting point and connect like so, that would be vector v plus w, which is called a resultant vector. So the wind, theoretically, made up example here, kind of pushed that airplane well off course. And that's called a triangle method. That's the preferred method you'll find in most physics classes where vectors really get used predominantly in the future. Other definitions, opposites. Vectors are opposite of each other if they have the same magnitude but go the exact opposite way. So G and H, looking at these, same size vector, but the arrow's on the opposite end. I and J, again, the exact same size of vector, but the arrow's on the opposite edges of each other. Scalar. Scalar is when you multiply the magnitude of the vector, when you increase the size of it, increase or decrease the size of a vector. So for instance here, we have big old vector B, and if you notice, we have small vector A. B is really just 3 A's pieced together. So we could say vector B is 3 times vector A. B is 3 of A, where 3 is that scalar. Again, a scalar is a, multiply the magnitude, multiply the size of a vector. This vector C down here is definitely bigger than vector A. If you look at it closely, it's 2 of these A's. Vector C is twice the size of vector A, but also notice the arrow is on the wrong end. It's on the opposite end. So we denote that by a negative sign. So vector C is 2 vector A's. Opposite means it's a negative 2 vector A. I should have highlighted that up top here. I and J are opposite. I is negative J, or J is negative I. And if we want to flip the terminal point, the end of a vector, it has to become a negative of itself. All right, so that's a lot of geometric. Not going to run through this one. We tend to live in the more algebraic realm of vectors. So right here, we have several vectors laid out. Focusing on this one at the beginning. That vector starts at 0, 0 and stops at 3, 5. So I'm going to say over here, the initial point of this particular vector that I'm circling now is 0, 0. The terminal point is at 3, 5. And notation and symbolism is where a lot of mistakes happen right now. I'm putting parentheses, a traditional parenthesis around 0, 0 and 3, 5, because those are points. They are dots on this grid. They are dots in space. They are not representing how far something has traveled. The vector then is how far do you move between those points. And vectors have horizontal and vertical components. Horizontal means how far does this vector move towards the side. This vector is moving, let me get a better color, horizontally to the side, and it looks like we're moving 1, 2, 3 units. Or I start at 0 in the horizontal X position, we stop at 3 in the horizontal X position. From 0 to 3, we move 3 units. And then how far does this vector move vertically? Well, from bottom to top, we went 1, 2, 3, 4, 5 units up, or I started at 0 in the vertical Y position, and I stopped at 5 in the vertical Y position. From 0 to 5, we traveled through 5 units. The vector between those 2 points then is 3, 5. And to denote that, I don't use your traditional parentheses. I use the, I use the greater than, less than looking caret-like ordering units. So again, these particular symbols, the greater than, less than, caret looking symbols, that means it's a vector. That's not a point. That means we are moving 3 units horizontally and 5 units vertically. All of these vectors listed off to the side here in blue are 3, 5. They all start and stop in different locations, but if we look closely, I'll run through one of them. This vector is moving 3 units horizontally and 5 units vertically. That is vector 3, 5. Again, I use greater than, less than looking symbols around the 3 and 5 to denote that it's not a point, that's a vector. This is not at position 3, 5. It has moved 3 units horizontally, 5 units vertically. Same thing here. This vector has moved 1, 2, 3 units horizontally, 1, 2, 3, 4, 5 units vertically. So this is vector 3, 5. Now, if I think of vectors that way, as far as horizontal and vertical movement, we can find the size of that. So again, if we move horizontally, that's the X position we move, and we also move vertically, that's your Y position. The size of this vector is called the magnitude. We can clearly see we make a right triangle out of this. And if you have a right triangle, the famous Pythagorean theorem lets you find the missing piece of any side of a right triangle. So we could say the horizontal, the X side squared, plus the vertical, the Y side squared, has to equal this hypotenuse, which happens to be the magnitude of our vector, the size of that vector. So the magnitude squared. If I want just the magnitude, I can take the square root, and you have a convenient x squared plus y squared square root is the magnitude of any vector. So again, this is big to know. Radical x squared plus y squared is the magnitude of a vector. Radical x squared plus y squared is the magnitude of any vector. So now we're given point X, -3, 5, point Y, 4, -2. What is the vector between those points, and what is the size? What is the magnitude of that vector? So again, these are points. Those are not vectors. Those are dots on a grid. And I know they're points because you have a parenthesis around those numbers. I can figure out the vector if I figure out, so again, vector xy is going to be how far do you move horizontally and how far do you move vertically between those 2 points, because vectors are how far you're moving. If I'm at -3 and I move to +4, if I go from -3 to +4, that means I move 7 units. So I move 7 units horizontally. If we're at a +5 and we move to -2, we've traveled down 7 units. We went backward 7 units. So that's a -7. So vector xy has the caret greater than, less than symbols around it. It's going 7 units horizontally, -7 units vertically. That's the vector between those points. We can find the magnitude of that vector then. How large is it? And I can say the magnitude is this double absolute value symbol. It's going to be radical 7 squared plus -7 squared. And on these, a lot of times a rounded decimal is fine on vectors. Typically, we want to know it makes more sense to us to have a decimal equivalent. So I'm going to say that this is 7 squared plus -7 squared, which is going to give us about 9.9. I think. Let me do that again. Yep. 9.9-ish. Again, that just means this vector is about 9.9 units long. Okay, and again, I knew these were points. The parentheses mean those are 2 dots in space. The vector between those is what we just figured out. As far as maybe a sketch, a picture of that. Again, we just figured out 1, 2, 3, 1, 2, 3, 4, 5. We have a point X at -3, +5, and a point Y at +4, -2. Connecting those points, that's the vector. We went 7 units horizontally, down 7 units vertically, and this vector is 9.9 units long. All righty. Now, if things are in vector form, we can do some basic operations. We don't need to make triangle methods and parallelogram methods from before. If I want to do vector M plus vector P. Again, notice up top in the stem, I'm given M, and I know that this is a vector because A, the symbol above the M is a vector symbol, and the 5 and -7 are in the greater than, less than, caret looking symbols. Those are not points, those are not dots. Vector N, again, that's a vector because the symbols around the 0 and the 4, and then vector P is -1, 3 because of the symbols around the -1 and the 3. They're not a traditional parenthesis. M plus P, we just add or subtract like components. So what I mean by that, M plus P here is going to be take 5 for the X component plus a -1 in vector P for that X component. So the 5 and the -1 go together, comma, the Y is a -7 plus a +3. So the resultant vector of these, R for resultant, if you add or subtract or manipulate vectors, it becomes a resultant. We get 4, -4. M minus P, same situation except subtract these. So M is a 5 minus P is a -1. So 5 minus -1 and -7 minus +3 gives us a resultant vector of 6, -10. A scalar, this 7 out in front means multiply the components of vector P by a 7. So the resultant here would be 7 times a -1. It's a -7. 7 times 3 is a 21. And finally, order of operations come into play for a larger case like 2m plus 3n minus p. This is asking you to do 2 times vector m, 2 times 5, -7, plus 3 times vector n, which is 0, 4, minus a vector p, -1, 3. That's going to be 10, -14, plus 0, 12, minus -1, 3. And then moving from right to left, or left to right, sorry. 10 plus 0 is 10, minus -1 is 11. -14 plus 12 is -2, minus 3 is a -5. 10, 0, it's 11. -14 plus 12 is -2, minus 3, -5. I think we're right, 11, -5. Okay. And last, unit vector form. This is just another notation symbol. A unit vector is a vector with magnitude of 1. What is that doing there? So basically, I is 1 horizontal unit, and j is 1 vertical unit. So over here, vector I moves 1 unit horizontally, vector j moves 1 unit vertically. Right, AB is the sum of unit vectors. That just means use I and j to denote these. This is a point. There's a parenthesis around 4, -1, and a parenthesis around 6, +2. I cannot add this up. I do not say 4 plus 6 is 10, -1 plus 2 is 1. These are not vectors. I can't just add and subtract the components. I need to know what is the vector between those 2 points. So if I move from 4 to 6, 4 to 6 means I move 2 units horizontally. If I move from -1 to 2, -1 to 2 means we move 3 units vertically. This is the ordered pair way of writing a vector, what we've done up until now. If I want to write this in unit vector form, instead of 2, 3 inside greater than less than, I'm going to say 2 is the horizontal. So I have 2 I vectors plus 3 is the vertical, 3 j vectors. I is your horizontal, j is your vertical, 2i plus 3j. This is the sum of unit vectors. And I guess one more time, just to do this again, have another example of it. It could ask you, what is the magnitude of AB? Again, this double absolute value symbol means the magnitude. And we find that by taking the square root of the horizontal, the x, so the 2 squared, plus the vertical, the j, 3 squared. Radical 2 squared plus 3 squared is radical 13, which is about 3.6. So again, that's kind of a quick overview of just vector basics. Big mistakes in the past have been, again, not understanding that a parenthesis means that's a point in space, a dot. These carets means that's a vector. That now means how far are you moving. 2, 3 doesn't mean you're at 2, 3 on the grid. It means you've moved 2 units and 3 units. All right, guys. We will continue on Wednesday with some different ideas on how do you change ways in which to write a vector, represent a vector. I would like you guys to try and check in the back of the book. Make sure we're okay with this. Page 606, number 25 to 43 odd. You will have a quiz on Friday this week in Schoology. I'll cover some of this material. Wednesday, we'll have a new lesson. Wednesday's assignment will be a Schoology-based assignment you'll need to do on Schoology and submit. And again, Friday's quiz will cover the stuff from today and Wednesday. Hope you're all doing well. If you got any questions, let me know. Hit me up on Schoology. Otherwise, signing out.